All right, welcome. Today, we're going to crack open one of the most fundamental forces in our modern world, electric current. We're going to break down what it is, how we measure it, and even peek into the microscopic dance of electrons that makes it all happen.
You know, think about this for a second. You flip a switch, and bam, a light turns on across the room. Instantly. It feels like magic, right? But it's all just incredible physics. So what is actually going on inside those wires at that exact moment? Let's find out.
So, here's our game plan for this explainer. We'll start with the basics. What is electric current? Then we'll get into a pretty fascinating historical mix-up called a tale of two currents. After that, we'll zoom way in to see what's happening inside the conductor, put our new knowledge to the test with some real physics problems, and finally, we'll do a quick check to see what you've learned.
All right, let's kick things off at the very beginning. At its heart, electricity is really just about one thing: the movement of charge.
So the official definition is this. Electric current, and we use the letter I for it, is simply the rate of flow of electric charge. We measure this flow in amperes, or just amps for short, named after the legend himself, André-Marie Ampere.
And that definition leads us right to our first super important equation, I equals Q divided by T. Here, I is our current in amps. Q is the total amount of charge, which we measure in coulombs, and T is how much time it takes for that charge to pass by. Pretty simple, right?
Okay, to really get a feel for this, let's use an analogy. Picture the electric charges, these tiny electrons, as marbles. The copper wire is just a long, thin pipe that's already full of these marbles. Now, if you were an ammeter, your only job would be to stand at one spot on the pipe and count how many marbles roll past you every single second. That number, the rate of marbles, is your current.
Now, for a little bit of history, because this is where things get interesting. It turns out that the scientists who first studied electricity made a totally reasonable guess about which way it was flowing. But they got it completely backward. And, well, the convention just stuck. Way back, Benjamin Franklin imagined electricity as this kind of invisible fluid. He figured it flowed from a place with a positive charge to a place with a negative charge. And hey, that makes perfect sense. The problem was, it wasn't until much later that J.J. Thomson actually discovered the electron and proved that in metal wires, it's these tiny negatively charged electrons that do all the moving, and they flow from negative to positive.
So this leaves us with two models that we still use today. First, there's conventional current. That's Ben Franklin's idea, flowing from positive to negative. And for the sake of tradition and simplicity, it's what we still use in every single circuit diagram. Then there's electron flow, which describes what's really happening physically inside the metal. Electrons are moving from the negative end to the positive end. The most important thing for you to remember is this. When we draw and solve circuits, we always use conventional current, even though we know the electrons are actually going the other way.
All right, now we're going to zoom way in. We're going from the big picture view of the wire down to the microscopic level to talk about something called drift velocity.
So check out this diagram. It shows exactly what we were just talking about. Look at the top part, A. See how it shows positive charges moving from left to right? That's our conventional current. Now look at the bottom diagram, B. This is the physical reality in a wire. All these little negative electrons are actually moving from right to left, but they still create an effective current that flows to the right.
And here's what's so cool. We can actually connect the big picture current we measure to this tiny microscopic dance of electrons with one really powerful equation. Let's break down the parts. I is our current. A is the cross-sectional area, basically how thick the wire is. A fatter wire means more room for charges. N is how many charge carriers are packed into a certain volume of the material. V is the drift speed, how fast those carriers are actually moving. And Q is the charge on each individual carrier.
So when you put all of those pieces together, you get this. I equals A times N times V times Q. This formula is amazing because it directly links the current we can easily measure with an ammeter to all these tiny properties of the material itself.
Okay, theory is one thing, but let's actually put this stuff to work and see how these equations play out by tackling a couple of examples straight from the textbook.
Let's start with a nice, straightforward one. We've got a simple torch bulb. We know the current is 0.03 amps, and the question is, how much total charge flows through that bulb in 1 minute?
So to crack this, we just flip our first equation around to solve for Q. Now the classic trip-up spot here is the units. Physics formulas need standard units, so we have to convert that 1 minute into 60 seconds. Once we do that, we just multiply 0.03 amps by 60 seconds, and we get our answer, 1.8 coulombs of charge. Easy enough.
Okay, ready to level up?
This next one uses that big drift velocity equation. We've got a copper wire, and we're given the current, its dimensions, and how dense the charge carriers are. Our mission is to figure out the average speed of the electrons themselves.
Just like before, we're going to rearrange the formula to find what we're looking for, which is the speed, v. And again, watch out for those units. We've got to get the area from square millimeters into square meters. Once all the numbers are plugged in correctly, we calculate the answer and, whoa, it's 1.2 times 10 to the minus 4 meters per second. That is insanely slow. It's less than a millimeter per second. Now, hold that thought.
Phew, we've covered a ton. So let's do a quick knowledge check with a couple of questions to make sure the really important ideas stick.
Okay, this is probably the most important thing to walk away with today. After everything we've talked about, what is the fundamental definition of electric current?
You got it. The rate of flow of electric charge. It's that simple, but so powerful. If you remember nothing else, remember that.
All right, and for our final thought, let's go back to that crazy slow speed we just calculated. If the individual electrons are moving at a snail's pace, how on earth does a light bulb turn on the very instant you flip a switch? Well, remember those marbles in the pipe? The pipe is already full of them from one end to the other. The moment you push a new marble in one end, another one is forced out the other end almost immediately. The whole column of marbles moves together. And that is the real magic behind why your lights turn on in an instant.